Hi everyone. So today we'll be discussing the paper. The paper is titled Exploring Graph-Based Knowledge, Multi-Level Feature Distillation via a Channel's Relational Graph. So first, let's understand what the title actually talks about. So graph-based knowledge refers to using a graph in order to represent the knowledge inside the neural network. We'll understand what knowledge actually means later on. Multi-level feature distillation refers to the several feature maps inside the neural network. For example, each layer out here is a feature map, and therefore it's called a multi-layer feature map. And the channel's relational graph is a graph which would help us understand the relationship between each of these layers. So that's the title. But to understand the title, we need to understand what exactly the paper is talking about and what issues the paper is trying to handle. So oftentimes, the neural networks can become extremely large and complicated. For example, in this case, as you can see, the neural network is really large. In GPT-3, we nearly have 175 billion parameters, the neural network. Recommendation systems such as Netflix and Amazon also has really large neural networks. So the issue with having large neural networks is that we can't use them when we do not have enough resources. So a solution to such a problem is to train these extremely large neural networks, but we do not deploy them. Instead, we deploy a really small neural network and we transfer the knowledge that is encoded in the really large neural network into the smaller student network, right? This is called knowledge diffusion. Sorry, this is called knowledge distillation, and this was introduced by Geoffrey Hinton in his paper titled Distilling Knowledge in a Neural Network. This paper was published in 2015. So in this case, we have a really large teacher model, as you can see here, and we have a small student model. Our main goal is for the student model, which would be a lot more efficient, to produce the same output as the teacher model, right? So that we can deploy the student model in areas where we have less resources. So an example of this in real life is to understand that the features that are required while training for a model are different from the features that are required for deployment. For example, let's say when you're a child, your requirements are way different from those when you're an adult, right? So, however, the goal in these two cases remains the same. The goal is for the student model to provide the same outputs as the teacher model, right? So we want the student model in order to generalize the same way as the teacher model. The way this works is first we train the teacher model, which is extremely large and complex, and then we transfer or distill the knowledge into the student model so that it becomes more suitable for deployment, right? So we've been talking about knowledge quite often. So first, let's try to understand what exactly knowledge refers to. Knowledge oftentimes is interpreted as the parameters or the weights and biases inside the neural network, but that is not the case. We can think of knowledge as a set of mappings between the input vector and the output vector. So this would help us this would help us in understanding how we can train a different form of model to provide us with the same output. So the key idea in Hinton's paper was to apply the probabilities that were used as a result of the teacher model and to train the student model such that it provides us with the exact same probabilities as the teacher model. So what you see here is y1, y2 till yc, which are the logits. These logits refer to the output that is produced as a result of the last layer in the neural network. After that, we apply the softmax function in order to achieve probabilities for each of these logits, right? So the softmax function is a function that is defined as follows. The main use of the softmax function is to get a probability distribution. So with the help of this probability distribution, we can help train the student model to match the teacher model, and therefore the student model will start generalizing data the same way as the student model. So the various steps in this would be to first train the teacher model, then you generate the soft targets, which are these, the probabilities that the teacher model would give us. After that, we would train the student model on the original data plus the soft targets that were generated as a result of the teacher model, right? And finally, we would want to optimize the loss function. This loss function has two parts. It consists of the original loss, which is the difference between the data and the output, and the loss in terms of the relationship between the student and the teacher. So this was what was covered in Hinton's paper. There were other forms of knowledge distillation that were also employed. Another way of knowledge distillation is to use the intermediate representations of a model. For example, as you can see here, an elephant has been broken down into several features inside the elephant. For example, we have a straight line, then we have a squiggly line, and then all the way up to an elephant. This refers to various features inside the model. So we can also train the student model.
I'm sorry, yeah, I have a question. I have no idea what the logic is.
Huh?
Could you explain?
Oh, so
So like it was a bit up before that. Yeah, this one.
this one?
Yeah, like there were logits and.
Okay, so there'll be an output that you get from the last layer of the neural network, right? So just that, the raw output is called the logit. After you apply this function, which is the softmax function, which is this.
Yeah.
So this is a function that you apply to each of the logits.
Oh, okay, makes sense. Yeah.
You'll get the probability distribution, which would give us probabilities.
Thank you very much.
You're welcome.
So one question I have is like, applying the softmax is sort of like classification problem, right?
Yeah.
For example, like in a regression problem, how does that? You usually don't apply the softmax function for regression. For example, like object detection, you have like classification part as well as regression part for bounding boxes, right? So how do you calculate that?
We're
Right now for like this is just for the classification. Right.
Right. So now we are talking about how we'd use the intermediate representations of an image in order to train the student model to match the teacher model. For example, in this case, the elephant has several features that have been represented out here. This was covered in the paper titled FitNets, Hints for Thin Deep Nets. In this, the intermediate representation of the data, the intermediate layers of the data is used in order to train the student such that it can match the teacher. In this case, the hint that is referred to out here is the output of the teacher model that is used to guide the student model. Another way of knowledge distillation that was used is in this paper, where titled Paying More Attention to Attention, in which we mainly use the attention mechanisms of the teacher in order to match those of the student. For example, in this case, this is an attention map of the input image. And the attention map is mainly used in order to focus on specific parts of the data. So we can train the students such that the attention maps of the student and those of the teacher align with each other. Again, this and the previous ones have several issues because the student might not understand which areas in the teacher are important. Therefore, we also need to consider the relationship inside the, sorry. One sec. Right. So this denotes the feature distillation using the intermediate layers, and this denotes the feature distillation using just the logic distillation, which is just the output. This involves those using just the attention map. So this covered some of the previous works in knowledge distillation. So the paper talks about another form of knowledge distillation in which we mainly focus on the graph or the relationship between the nodes and the edges formed in the graph. So in this case, one sec. So in this case, the node would correspond to the channel inside the teacher, and the edge would denote the similarity between two channels inside the teacher. We can use this.
So yeah, could you please go back to that picture? It was yeah. So my question is, can this matrix become too big? Like, basically, if we just naively store that matrix, it would be a square of values, right? So
Right. So to not make it big, we'll be using a method called dimensionality reduction. In that case, we would just be using the largest eigenvalues inside the matrix, largest n eigenvalues, let's say, such that we can reduce the amount of data without causing any loss of information in the data.
oh, okay.
So that's how we would prevent the matrix from becoming too big.
I also have another question. Like I've seen recently like Google Gemini, they use knowledge distillation to kind of make to kind of enter smaller models called Gemini Nano. I was wondering if you have any idea of like how much smaller can they really make it? Like is it like 1/10 of the size or?
I'm not sure how much smaller the student model becomes in comparison to the teacher model. Anybody has any idea? No. Sure.
How exactly does finding the eigenvalues help us?
Finding the eigenvalues of the matrix. So a matrix that is symmetric, you can perform an eigenvalue decomposition in order to get the eigenvalues, right? So the eigenvector, so the matrix that's in between, that's formed of the eigenvalues, that would help us get the original matrix. Therefore, if we just take the top n values of them, that'll encode some of the information that's already present inside the matrix. I mean, we'll obviously lose some information, but our main aim is not to make the matrix big while at the same time storing some information.
Okay.
So that's how we use the eigenvalues inside the matrix.
Isn't it pretty computationally intensive to like calculate the eigenvalues in like a large matrix?
I'm not sure about that
Like-
because I'm not sure.
I think it is, but like over here, we make sure that the matrices we calculate are like symmetric, and we also have some other techniques to reduce the dimensions as well.
Right, so the main thing in this case is that the matrix that we're using is symmetric. That's something that we'd be focusing on. So
Also, like it's still much cheaper than like making a very large model.
right. So let's focus on what exactly is going on here, because this image doesn't make much sense. So as I said, we would have the teacher model out here. We would have the student model. Each teacher model has a feature map, has a set of feature maps, where each feature map corresponds to a particular feature in the image. And the student consists of a set of feature maps as well. Then we'd be using two attention masks, a spatial attention mask and a channel attention mask. So to understand what a spatial attention mask actually gives you, so an attention mask helps us highlight important features inside the matrix itself. So this would help us highlight particular regions of interest to us. This is what an attention mask gives us. So in this case, the spatial attention mask gives us the important regions inside each matrix. The channel attention mask will give us the important channel inside the set of all channels. After that, we would use these in order to get a vertex loss. Right. So first, let's understand what a vertex edge is in this case. So the graph consists of teacher channels where each teacher channel is a vertex, and the edge denotes the similarity between two teacher channels. So that's exactly what the graph is, as you can see here. B consists of the various channels, and the edge represents how similar two channels are. To mathematically represent this edge, we'll be using a weighted adjacency matrix. And a weighted adjacency matrix is something like this, as you can see here, where each entry in this case denotes the weight for each edge. And to get the value of the entry inside to get the value of the entry in the adjacency matrix, we would use something known as cosine similarity. You can think of this as just finding the cost of the angle between two feature maps. However, in this case, each feature map is a matrix of dimension W cross H. So first, we need to vectorize each feature map. By vectorize, I mean we need to convert it into a single vector, which is of length W cross H. So after we have two vectors of length W cross H, we just compute the cosine of the angle between them in order to get each entry inside the adjacency matrix. So now we have the vertex set, we have the edge set, we have established what exactly the graph is right now.
I think you talked about the graph, but could you like give an example, for example, for the image which is showed above? Like what exactly would the graph contain?
Right. So in this image, so first, if you pass it through a neural network, right? There would be several feature maps. By feature maps, I meant each feature map denotes a particular feature inside the image. Let's say this feature map, a feature map could say give the eyes of the dog, or let's say the ears of the dog. So in that case, each feature would denote the vertex, and the weight between two vertices would be how similar these two features are inside the image. So that's an example of how it would be in the case of an image.
So this might be a dumb question, but are feature maps generated after each layer?
Yeah, so they just denote each layer basically.
Okay.
That's pretty much a feature map. A feature map is just the layer inside the inside the neural network.
Do you make each layer a node in the graph? Or
Yeah. So each layer is a node in the graph, and how similar two layers are to each other is pretty much the weight inside the graph.
Wait,
so
I
do
think
you
like,
expect to see like adjacent layers to be more similar?
See?
In general, like adjacent layers, you would expect them to be more similar.
Adjacent layers, like layers that are close to each other.
Yeah, because it would like probably try to find like high level features to low level features. So
Oh yeah, so that makes sense, yes. So
so adjacent ones are always
should have a
more
higher
similar to
weight.
each other.
Yeah, so they should have a higher weight in this case.
but in this case, like, I thought you're making the graphs per layer, right? So for a particular layer, you have C number of feature maps, right?
No, the graph is not per layer. The graph,
Yeah.
the graph encodes all the feature maps.
Feature maps of all the layers.
Yes.
So for example, like if you take a ResNet or something like that, so if you take a particular layer, it will have like 256, 512 feature maps for a particular layer, right?
Right.
So you are saying like all of them are sort of like concatenated, and that's going to be the input to the graph.
Right.
So how do you like change the dimensions of the features? Because as you move from higher layer to a lower layer, the resolution drops.
I think this is more for a single layer.
Yeah, that's what I thought as well.
Yeah, because they're
You are
given the-
creating graphs per layer.
Because they're given the thing at C cross H cross W.
Yeah,
So
C
for it to be
denotes the
uniform, it
number
needs
of
to be
feature maps
one
per
layer.
layer.
Yeah.
Because otherwise you won't have a fixed WH across the layers.
Yeah, it says like if you go to 2.1, on the first 2.1 session, like we look
Right.
can you go and scroll down?
Yeah.
Yeah. So 2.1 first line it says we use F to denote the feature maps from one layer of the graph. So it's just from one layer.
Okay, right.
How do you choose the layers for actually doing the distillation? Is it like some intelligent way, or is it just like choose the same resolution layers?
I'm not sure. The paper doesn't talk about it.
Wait, but I still think it's one graph that's generated, no? Because
I thought it was one graph.
Yeah,
actually.
graph is one only, but it's for each layer.
Okay, for one layer, you're creating one graph, and you're sort of like calculating the similarity between one layer of the teacher map to the student's network, right?
So probably you would have to run this like
Multiple times.
Yeah. Yeah, the problem is how you are choosing which layer to be mapped
Yeah.
in the teacher map, right? So
That's. Yeah, I'm not sure if they talk about that.
maybe the loss function might be that.
No, in the loss function, they just talk about this particular graph, just for one graph.
Just the two graphs.
Right. So as you like in the loss function, if you look at it, it's just one loss function that's for this particular feature map, right? If I'm not wrong. As you can see here, right?
Yeah, in this paper they just talk about one graph to one graph. They don't really detail about how they go about it.
Right. So so there are just two loss functions out here. There's a vertex loss and then there's an edge loss. To get the vertex loss, So to understand what exactly the vertex loss is, the vertex loss should first have the difference between the vertices between the difference between each element inside the map of the teacher and each element inside the student, right? So this is what that says. And we need to multiply it by how much weight we must assign to each element inside, how much weight we must assign to each thing, right? So to get how much weight we must assign, we must understand how important each is. So that we get by using attention masks, which are of two kinds, the spatial attention mask and the channel attention mask. The spatial attention mask would give us the most important region inside the channel. The channel attention mask would give us the most important channel out of all the channels. You can intuitively understand why this is the case. So the stuff inside the softmax function is the aggregate of all the feature maps. So this can be thought of as the average channel, and applying softmax to it helps us get the most important region inside the map, right? So this would help us understand what the spatial attention mask is. Then to get the channel attention mask, again, we need to understand how much weight we must give to each channel. This can be understood by taking the average of the entries inside the feature map. So, and then again applying softmax to it to get the weight, and therefore we have the channel attention mask now. So now we have the spatial attention mask, we have the channel attention mask, and therefore we can easily compute the loss function for the vertex by assigning it this much weight.
So over here, I see that you have multiplied with H, W, and C in equation 3, and then you again divide by that in equation 5. So is there like any purpose to this, or it's some kind of standard notation?
I was talking to Rishit about why we multiply by HW and why we multiply by C, and I think he understands it better.
Oh, I was just like, I just thought it was to make the variance one, just standard, so.
Okay.
So why don't you use a graph-based approach for knowledge distribution?
Not
just a simple model.
So we use the graph in order to get the relationship between two channels, basically. There will be no other way apart from that to get the relationship. So graph would help us understand the relationship. And then finally, we'll compute the edge loss. So in order to get the edge loss, we'd be using the adjacency matrix, and we'd be multiplying it by how important the difference between each entry is. And to get the importance or the weight, we'd be using the relational attention mask, as you can see here. The relational attention mask helps us, is just the softmax of A. So we assign enough weight to the important edges. Therefore, we get the edge loss, we get the vertex loss. Now, after these two losses, this is the important part of the paper. This is what's important in this paper, because spectral embedding is used in this paper. So as I was saying, spectral embedding is a form of dimensionality reduction. And by dimensionality reduction, it is so that the high dimensional data can be clustered together. So as I said, we first represent the data as a graph, and then we just take the top n eigenvectors of a specific matrix. And by taking the largest n largest n eigenvalues and getting the eigenvectors corresponding to them, we would be able to encode information about the graph. So, so how we compute the loss, the spectral embedding loss is as follows. First, we compute the degree matrix. So the degree matrix can be thought of as the sum of the columns of each entry, and this would be a diagonal matrix. So this is the degree matrix. Then we have the symmetric normalized Laplacian, which is denoted by the formula given here. There are actually two forms of Laplacians. There's the normalized Laplacian, and then there's the unnormalized Laplacian. The unnormalized Laplacian just is L equals D minus A. We don't want to use that one because in that we'd have issues when there are nodes which have a lot more edges, and those would have a lot more weight when they shouldn't be having a lot more weight. So we instead use the normalized Laplacian matrix. After that,
So are there any other forms of equation used as well, or is it just
right, like I said, we can use L equals D minus A as well, which is the degree matrix minus the adjacency matrix. But in that case, nodes which will have more edges incident on them would have more weight in that Laplacian matrix. And we don't want that to happen. So that
because B in somewhere represents like a total weight of the edges, like connecting a node, right?
right.
Okay.
So that is called the unnormalized Laplacian matrix. So and we don't want to use that. So we instead use the symmetric Laplacian matrix.
One more question.
Sure.
So if there is a matrix with the power of minus 1 over 2, it's like 1 over the square root of b, right?
Hmm.
So like how do we usually compute that power? So it's like, is it using spectral resolution or something?
So we have some techniques such as like spectral value decomposition, and you can look up eigenvalue decomposition. You will find a lot of literature on it and how it is implemented in code and stuff. So there has been a lot of research to make this faster.
Oh, okay.
Like when we say to the power of negative 1 over 2, we don't actually square root it and actually invert it. There are other methods to compute.
Oh, okay. It's good to know. Thank you.
Right. So as I said, we get the largest eigenvalues, the n largest eigenvalues, and then we get the eigenvectors corresponding to those eigenvalues. And finally, we have the spectral embedding loss, which is defined by this function out here. And I think this makes sense because we have n eigenvectors, and we have each is of dimension c. Therefore, this is the spectral embedding loss. Finally, we have the actual loss that we are interested in, which consists of the multi-level feature loss and the overall loss. So after having gotten the vertex loss, the edge loss, and the spectral embedding loss, the multi-level feature loss is just a function of the vertex, edge, and the spectral embedding. So alpha, beta, gamma are called hyperparameters, and we'd be running experiments to find out which value of alpha, beta, gamma would be the most suitable. Finally, we get the global loss function, which is L total, which is denoted by the multi-level feature loss plus the original loss. This original loss is pretty much the same as those that we have in machine learning, which is just the result that is predicted by the model and the ground truth, the difference between that. So we have the total loss in this case. Now let's see.
Whose original loss are we taking? Is it teachers one or students?
We want the students, so we're training the student, right? We have already trained the teacher.
The students.
Students, right? because we have already trained the teacher and now we're mainly focusing on the student right now. So, right, one second.
Isn't this just regularizing the algorithm?
Sorry?
So this is just like some intelligent regularization for algorithm, right?
Right, because our main goal is to train the student, and so we don't want the student to be as complicated as the teacher. So we already have trained this teacher, so we take some information from the teacher already, and we try to use it for the student as well, so that we can train the student. So that's how that's the method that they're using for this. And to see the results, you can see that the result that is produced by this paper is much better than those that have been produced by previous such papers. And therefore, this clearly has done a good job in this case.
I see that in some cases it's actually performs better than the teacher itself. How is that? That's a bit weird.
Huh.
How much smaller is the student model here?
I'm not sure. The paper doesn't discuss about how much smaller the student model is.
It's really big, like even in the algorithm, I'm saying the feature maps of the student and teacher from layers 1 to L. So both of them are sort of like having the L number of net layers.
Actually,
I don't know how they are decision.
I guess there are some flaws of the paper. So this paper was released like just last week.
Okay.
On archive. So generally we try to discuss like really recent papers. So there are many times there are some flaws with the paper. So
Tell us how much smaller the number is.
yeah, maybe they'll get that from the reviewer to comment and ask it.
but probably it's not a flow, it's just in the appendix.
Maybe.
Yeah, no, that's right.
All right. So let's just look at some of the limitations in this study.
And how does he like training for the distillation work? This isn't like an Adamax problem. So what do they use for like those results?
I'm sorry, I don't understand.
What would it be about the
Training.
Oh, like how do they exactly train? How do they exactly do the training for the distillation?
Like train the student?
Probably they have that information in the appendix. Yeah, see over here they give like results per layer as well. That's how you were talking about the limitation.
Right. Some of the limitations are that it is clearly subjective to which channel they think is important and which feature maps they think are important. And another limitation is that they're using spectral embedding for dimensionality reduction, whereas they could be using any other method for dimensionality reduction. And I would like to know what happens if they use any other methods for dimensionality reduction.
So how scalable is your approach when compared to bigger and more complex data sets?
Mm,
Like what scalability needs to use?
I'm not sure. I don't think the paper talks about it.
I can see in the appendix they're actually giving the training costs for different models. Like I see like ResNet and stuff. It's about like 10 to 15 hours.
So are the experiments like for object detection?
Yeah, it's mainly for object detection.
I thought like the method was describing how to do it for classification. If I didn't.
We're working with
Just do it like for the classification branch in object detection?
It is classification. I guess.
No, so the MS Coco and Pascal.
MS Coco is
For object detection.
Yeah, it's over there.
So
Like
Command
MS
Ready
Coco
is
is
on
for
for the
object
classification.
detection,
and Pascal is used for classification.
and CFAR they are using for classification.
Are the experiments like, do you also like use the method for like the regression branch of object detection or just like the classification branch? Because I thought like the approach you described seemed like
Well,
classification.
yeah, well, the regression part comes at the end, right? So object detection does the
Yeah.
regression. So in here, I guess the distillation happens within the internal layers, which are sort of like CNN kind of.
I see.
So it's not going to change in that. So they are not changing the method for regression and classification kind of thing. They are still in the internal layers. So the final, the L origin thing is the sum of the regression loss plus the classification.
So, I mean, that's it for the paper. If you guys have anything to talk about.
I have one question. So you just mentioned that the fact that they use spectral embedding is like a limitation.
I mean, it's not exactly a limitation because it is the most used, but I'd like to see what happens if they use another form. Oh.
Yeah, I mean, in the abstract, they're like, yeah, this is a key technique and like merges students' feature space with relational knowledge of structural complexities.
Yeah,
So doesn't that mean that it's
the
like they're
best.
presenting it as a strength?
Yeah, I definitely think it's a strength, but I would just like to see what happens if they use something else because
Okay.
it'd be interesting to see.
You would use student teacher distillation instead of just training the student. It's like for performance costs. Because imagine that like you just train the student on a virtual data set and you wouldn't have much loss of predictive power.
Right.
And you train it with the teacher.
Right. So the reason why we first need to train the teacher is because the data can like be extremely complex, right? And we might need an equally complex model to capture the complexity inside this data, which might not be captured by the student model, which would be much smaller and not as complicated as the teacher model. So the main thing that we're doing out here is like the teacher is being used in the training and the student model would be what would be deployed. And we want the student model to get the information that we got from the teacher and work with it, basically.
But then how would it get? It's like with less number of parameters, isn't it like necessarily going to be able to predict less than the teacher?
Yeah, that's true. But the thing is, like, we wanted to use much less space. Like, for example, you consider Google Gemini. I'm sure it's like a really big model, maybe hundreds of GB or something. I don't know. But nowadays, like with so many people are focusing on privacy, and they don't really want the AI to use the data on the cloud. So Google is like sort of coming up with AI that runs directly on your phone internally. So those models need to be like 2 or 3 GBs or like much smaller than the larger ones. And of course, they will perform a bit worse than they will perform considerably worse than the larger ones, but it is still something really important. And the thing is, like, the reason why we don't train an entirely smaller model is that it will just perform like really worse. Like over here, what we're trying to do is we are sort of trying to run the loss on each layer. So sort of we are teaching some particular layers of the student to behave like some particular layers of the teacher, which is slightly less intensive, and in a way it is it is kind of teaching it to learn similar features as the teacher model, which would simply not be possible if you train it directly on the data.
But so if you like just train it directly on the version data set, you're saying that the student will probably actually result in a worse model.
Yeah.
Because
it won't be able to learn that many features.
Intuitive way of saying it, it's like kind of you have some standard textbook like a just track Welsh textbook, and if you just get a fifth grader to read directly, you won't understand much. But you get like some professor to read it and intuitively explain it, essentially. They understand. That might be
the experiments they have here, is it starting from random initialization? Is it like trained for a little while or?
Um,
I think
I don't know
that
if
will
it's-
use some pre-training.
I think there's some pre-training.
Oh. And like what about the teacher then? Is it like pre-trained and then fine-tuned? Yeah, what's like the starting point for the student relative to the teacher? I don't know, the experiments, maybe I haven't read enough, but their experiments seem to be like.
Hmm.
Stuff you can get.
We get to know more once they release the code and stuff.
I know, like, like, the time to converge will depend on whether it's been pre-trained or initialized randomly. But in terms of the performance, it doesn't matter.
So, but it would be like an unfair comparison if the student model was like trained using some different techniques for like probably smaller models, there are like a lot of other techniques, and then you distill it and then show the comparison that it performs very well. Then that would be like maybe a not so great results table or not believable that this method changes a lot of stuff.
Right.
But maybe yeah, it's somewhere like in the appendix or somewhere. Maybe I need to read it.
If you all have some more questions about the math or that sort of, feel free to ask. I guess we are like, feel free to take some sandwiches and cookies home as well.